Let's go through an example of actually calculating the induced EMF and determining the direction of the current the direction of an induced current. So let's say that you have a 100 loop square coil of wire with a total resistance of 100 ohms, and it is sitting in a magnetic field of 0.6 teslas. You can see in the figure this magnetic field is indicated with the X's, which means the magnetic field is pointing into the screen that you're looking at right now. Let's take the square coil and pull it out of the field to the right in a time of 0.1 seconds. We want to find the change in magnetic flux. We want to find the induced EMF. We want to find the induced current. We also want to calculate the total force needed to overcome the magnetic force and actually be able to pull that loop out of the magnetic field. Let's start off by talking about the change in magnetic flux. Okay, we calculate the change in magnetic flux by looking at the change in the product of magnetic field times area times the cosine of theta. So we need to determine, first of all, what's changing. As the loop comes out, you're not turning the loop at all, so your angle theta stays the same. You're not deforming the loop, you're not changing its area at all, so area stays the same. Therefore, the magnetic field is what is changing. Before we do that, we need to also talk about the angle theta. What is the angle theta? Well, remember, that's the angle between the magnetic field and the vector for your area A, which is perpendicular to your surface. So you see your surface area A, that's the area inside of the loop, which is flat on your screen. So the vector A will be perpendicular, either coming out of or into the screen. We're going to say it's into. Okay, so your area A is parallel to your magnetic field, which means that your angle theta is going to be 0 degrees, because they are in the same direction. Okay, let's get back to our equation. Now that we've determined that, we have the change in magnetic field times area times cosine theta. We determined that what's changing is the magnetic field. The area and your angle theta are not changing. Okay, so let's plug in our values. Our magnetic field, change in magnetic field would be final minus initial. Final magnetic field would be indicated here 0, because it's moving over into this area where it's 0. But the initial was 0.6. Okay, so our change in magnetic field is 0 minus 0.6. Our area, it's a square, and the figure indicates that it is 5 centimeters on a side. So our area is going to be 5 centimeters, or 0.05 meters squared. Then multiply that by cosine of theta, where we determine that theta is equal to 0 degrees. Plug that all into your calculator. You see that there is a change in magnetic flux of negative 0.00150 Webers. That makes sense, because at first you have a magnetic field passing through the loop, but as the loop is pulled out, the magnetic field decreases, so there's less magnetic flux, so you have a negative change in magnetic flux. Oh good, so that makes sense. So let's move to the next point, and that is talking about the induced EMF. According to Faraday's law of induction, the induced EMF is going to equal negative N times the change in magnetic flux over the change in time. Well, we have all these. N is 100, because it's 100 loops. We just solved for the change in magnetic flux, negative 0.0015 Webers, and the time is given in the problem as 0.1 seconds. And so that gives us an induced EMF of positive 1.5 volts. All right. Induced current. Let's start off by calculating what is the value of the induced current, and then after that we'll talk about the direction of the induced current. So we use Ohm's law, that the voltage is equal to current times resistance. Current then is going to be the induced EMF divided by the resistance. Induced EMF we found in the last slide to be 1.5 volts. The problem tells us that the total resistance is 100 ohms. Therefore, the induced current is 0.015 amps. Okay, that's the magnitude of the induced current. What direction, though, is the current? Okay, remember from the previous video that the first step of determining the direction is, and applying Lenz's law, is to find out what's happening to the magnetic flux. Well, we saw back here that the magnetic flux is decreasing. Since the magnetic flux is decreasing, Lenz's law says that the induced current is going to oppose the change. It's going to create a magnetic field that re-increases the magnetic field. So that means that we need, let me get the right color here. We'll do that. Let's do this one here. No, that can't work either. We need a current that produces or induces a magnetic field going into the board. So my current produces a magnetic field that's going into the board. So use your right-hand rule, stick your thumb in the direction of the magnetic field. So point your right-hand thumb into the screen. Then your right-hand fingers should rotate in the direction, not should, they do rotate in the direction of your current, which means your current is flowing in this direction. So it's going clockwise. Excellent. So that's how to calculate the induced current and determine the direction of the same induced current. Let's go to the last point of this question, which is the force needed to overcome the magnetic force. Now, the force that you apply to extract the loop from the magnetic field must be at least that of the magnetic force. In other words, your applied force needs to be greater than or equal to your magnetic force. Magnetic force. Now, look in the field. The magnetic force is indicated as the force on the left. I also don't know why it's written as Fm. So we're going to say that that is Fb. That's the force exerted by the magnetic field on the left-hand side of the loop. Why just the left-hand side? Well, remember that the magnetic force is a result of a current passing through a magnetic field. We got that from chapter 20. Okay, and if you look at the electric current in this direction, use the right-hand rule, point your fingers right hand in the direction of the current, curl your fingers towards the magnetic field into the page. That creates a magnetic field that points to the left. Okay, but what about over here on the top or bottom sides of this loop, or for that matter on the right side? Well, the right side is easier to explain because that's going to be outside of the magnetic field. Therefore, there's going to be no magnetic force on the right side of the loop. On the bottom, if you do the right-hand rule, you find that there's a magnetic force pulling downward. And on the top of the loop, again, the right-hand rule shows that there's a magnetic force pointing upward. The current is the same, the magnetic field is the same, the length of wire exposed to the magnetic field is the same. Therefore, those two magnetic fields that I just drew here in green are equal and opposite. Therefore, they cancel out. That's why the picture only showed the one magnetic field on the left. Okay, so that's it for the explanation. Let's go to the calculation. Remember that for one wire, the magnetic force is going to equal the current in that wire times the length of that current, of that wire, times the magnetic field times the sine of theta. But we don't have one wire, we have n wires. Remember, it's a 100 loop square coil of wire. So you get the magnetic force ILB sine theta for each individual wire in the loop. But since there are n wires, you just multiply that by n, and that gives you the total magnetic force. Well, let's plug in all that information. N equals 100. Your current is 0.015 amps. The length of wire, that's the length of one side of the loop. That's 0.05 meters or 5 centimeters. Magnetic field is 0.6 Tesla. And the current is going up while the magnetic field is into the board. That gives us an angle of 90 degrees. Sine of 90 degrees is just 1. So calculate all that, and you get that there's a magnetic force of 0.045 newtons. Back to the question, how much force do you need to apply to overcome this magnetic force? Well, you need at least 0.045 newtons. If you have more than that, you can successfully pull it out. If you have less than 0.045 newtons, then the magnetic force is just going to pull that wire back into the magnetic field itself.